All right. So today we're going to work on pH practice problems, concentration estimation practice problems, and then two problems, one on page 115, one on page 118, that will get you ready for the quiz on Friday. So let's start out on page 114. Is there anything on the outside that you need me to explain? Anything that really stumps you? No? Feeling good on all these? I will say down here, if anybody's having trouble with the pH, pOH, concentration of OH minus, that kind of thing, you're going to want to look at page 113 at the bottom. That's where we did that one. All right, how about the inside? Anything that's really stumping anybody on the inside? Any left blank?
Only the part with the pH.
The part with the pH? Oh, at the end of this one?
Yes, ma'am.
Excellent. Let's work through that one. Okay, so the final problem on page 114 is at the very bottom of the page. And it basically said use all these skills, converting moles to grams, calculating calculating molarity, which is just moles divided by liters, and then going grams all the way to molarity using liters. Use that to figure out what is the concentration of hydronium ions. You'll also need stoichiometry for that. And then what's the pH. So let's work through that problem. Okay. Anytime we're doing stoichiometry, we are using a chemical reaction equation. So the first thing I like to do is copy down that and make sure that it's balanced. So we've got hydrogen fluoride plus water, and that is going to react to form H3O plus a fluoride ion. Now, this is technically exactly the same as if I'd written these guys react to form H plus F minus plus H3O. Oh, that should say H2O. Okay? It's exactly the same. Okay? So whenever you see H3O plus, you can treat it just like it's H plus. Everything we've learned is the same. This is still a thing that makes solutions acidic. The concentration of it is still the pH. Hello. We had a couple students walk in a little bit late. We're on page 115.
115?
115.
Perfect.
Okay.
This is the last one?
That's right. Before we continue on this one, do you need anything from earlier in the page?
Well, I have to finish this, but I'm going to do it when I get home.
Okay. And I'll tell you, the one we're about to do includes all of those things on the inside. It's just like putting them all together.
Okay.
So I'll actually, as I do these, I will go back out here and show you where the practice problems were for that step. So the problem asks you, if you have 10 grams of hydrogen fluoride and 2 liters of H2O, what is the pH going to be? Okay, if you mix those together. Now, we're going to assume that all of the hydrogen fluoride reacts, so none of it's left over. Every single molecule of this gets transformed into hydronium ions and fluoride ions. Okay? So let's start out with the first step. The very first thing we need is to take this 10 grams and convert it to moles. Because anytime we're doing a chemical reaction like this, all of this is in moles. Now let's take a look real quick. Is this reaction balanced? No, yes, we got lots of answers. Okay, let's find out. How many, let's see, we see hydrogen, fluorine, and oxygen on this side, and we see the same things on this side. How many hydrogen are on this side? 1, 2, 3. How many are on this side?
3.
How many fluorine are on this side?
1.
And over here?
1.
1. How many oxygen are on this side?
1.
And how many oxygen are on this side? Okay, the good news is that this whole thing is balanced then. And some people like to write the ones, some people don't like to write the ones. I'll leave it up to you, but I'm going to write them because we're going to use them later. So the first thing we need to do is, now that we've balanced this, we're going to convert grams of hydrogen fluoride to moles because we can't figure out anything about H3O plus in grams. If we want to get from hydrogen fluoride to hydronium, we need to go from grams to moles, and then we can go from there wherever we like. So first thing, we're going to convert grams of hydrogen fluoride to moles of hydrogen fluoride. And on the inside of page 114, this would be practice problems 1, 2, and 3. So if you're having trouble with these, maybe pause the video, open that up, do those practice problems, and then come back so that you know how to do this. Here we go. We always start out with whatever they gave us. Okay, so they gave us 10 grams, so we're going to start out with 10 grams of hydrogen fluoride. What should I do next? Okay, good. I have one student who's drawing furious X's in the air. Am I correct in assuming that what you'd like me to do is set up dimensional analysis? Yes, okay. So if we've got grams of hydrogen fluoride here and we want to get to moles, how do we set that up? We got grams, we want to get to moles. How are we going to do it? Good, grams on the bottom. Okay. And then what goes up here?
Moles.
Good. Okay, so what we need then is a ratio that will tell us how many grams are in 1 mole of hydrogen fluoride. And we can figure that out too. Hydrogen fluoride is made of 1 hydrogen and 1 fluoride ion. Hydrogen weighs 1.01 grams for every mole. And fluoride weighs 18.998 grams for every mole. If we add these together, we get the molecular mass of hydrogen fluoride. And I'm going to do a little bit of rounding here to make my life easier. But if you add these together, there's only one of each of them, so you don't have to do multiplication. This just ends up being 20.00 grams per mole.
You said for the F one it's 18.998.
Yeah, I got a little lazy with the math there. I added it together and then I rounded it. Okay, don't overthink it. At this point in chemistry, I'm not going to be taking off points for rounding errors. I'm way more concerned that you know how to get to the answer than that your answer is like exactly 0.0001 exact. So now that we've got our grams per mole, I want to show you something. When I say this, I always say, everybody look at the board, I always say grams per mole. We're going to do the same thing over here. It's just 20.00 grams per mole. That's what this line is. It's literally the same thing here. Anytime you see something like 20 grams per mole, you can plug it into a dimensional analysis problem just like this. Okay. So we're going to calculate an answer to that, and that's going to give us, let's see, it's going to be 10 divided by 20. So that's going to give us 0.50 moles of hydrogen fluoride. And we know that because the grams of hydrogen fluoride cancel out. How are you feeling so far? Good? Okay, I got some goods and some not goods. All right, what are we going to do next? Remember, our goal is to figure out the pH. So we need the concentration of H3O+. How do I get from moles of hydrogen fluoride to moles of H3O+? This is kind of a step 2. Oh no, we have a long way to go.
Is it gonna be like?
Yes, but it's going to be okay. It's going to be okay.
It's a formative problem.
It is. It's true.
Is there anywhere in the notes?
Yes, there are lots of places in the notes. If you,
Perfect.
yes, you may on this quiz you may use your notebook, and if you use your notebook, the max is going to be a 6. It's a 6. I changed it. You're
I
welcome.
don't even get any ideas about it.
So there is some stoichiometry on pages 94 and 95, and also on 92. 92 through 95 has stoichiometry on it. Okay, so we want to convert moles of hydrogen fluoride to what?
To the concentration.
Right. Eventually we want to get to the concentration of hydrogen ions, but that would mean we had to bring liters into the problem. So let's do it one step at a time. We know that it's asking for moles per liter. Let's convert it to moles, and we can divide by liters later. Moles of hydrogen fluoride to moles of H3O plus. Okay. So let's start with what we're given. Okay. 0.50 moles of hydrogen fluoride. All right, give me some bright ideas. How can we get moles of hydrogen fluoride to moles of H3O plus? Excellent. Dimensional analysis, we've got moles of hydrogen fluoride on the bottom. What goes on the top? Good. So now we need the numbers to plug in. Anytime you're trying to convert, actually I'll give you a second to think about this. Anytime you're trying to convert from moles of one thing to moles of another thing, you're going to need the chemical equation, the chemical reaction up here. Okay? So this is a recipe. It's a recipe just like, remember we did s'mores? If I have 1 graham cracker, how many s'mores can I make? 1. Assuming I have got plenty of everything else. If I got 1 graham cracker, I can make 1 s'more, yeah? What if I have 2 graham crackers? 2 s'mores. What if I have 365 graham crackers?
If you have enough the others.
A s'more a day for the whole year. And then diabetes. Yeah. So, if I have 1 mole of hydrogen fluoride, 1 mole of hydrogen fluoride, how many moles of hydronium am I going to make? 1, right. 1 mole of this will give me 1 mole of this, so we can just plug those in. Okay. And we'll do that conversion. Well, that's a pretty easy one. 0.5 times 1 divided by 1. There you go. 0.5 moles of H3O plus. Okay. This is going really well. So excited. The next step, we need to convert moles of H3O plus to a concentration of H3O plus. Because this is where we get pH. Okay. H3O plus, the concentration of H3O plus is the same thing as saying the capital M, which is the same thing as saying moles per liter. Okay. And this is, yeah, I know, this is the easy one. When we're converting from moles to moles per liter of something, we're going to need to know how many liters it's being dissolved in. The good news is these problems are really easy. These are problems 4, 5, and 6 on the homework. Don't overthink it. Moles is moles per liter, so you're just going to divide the number of moles by the number of liters every time.
Is on the test, is it going to be switched around? Like, for the last one, it was switched around for the moles and the liters. Like, the liters was like the first one.
Oh, let me show you that at the end. I'll show you how to do that.
Is it the same way? You just flip it regularly?
It's exactly the same thing. It's just a different way of solving the problem. I'll show you in just a second.
Okay.
So moles per liter, we have 0.50 moles of H3O plus. We're going to divide by the number of liters of water it's dissolved in. Okay, how many liters of water did they originally put these materials into?
8.
Not 5.
2 liters.
2 liters of H2O. And that's going to give us 0.25 molar solution of H3O plus. Which brings us to our final step. The question was, what's the pH of the solution going to be? So our last step is to estimate the pH. Okay, here's how we do this. Yeah? Oh, 1. Excellent. Walk us through it. How'd you get there? So we started with this. What did you do with it? Come in. We're recording, so figure it out. All right. So the first thing we need to do is convert it to something that looks like the pH problems we've been working with so far. We've got this on page 112. If the concentration of H plus is this, we convert it to a scientific notation, and then we can get the pH from it. So, who can convert this to scientific notation for us? Go ahead. 2.5 times 10 to the what?
-1.
-1, right, because we moved it 1 to the right. -1 moles of H3O plus. And then we can estimate pH by looking at the exponent there. So we know that the pH is about 1. Ta-da! You solved it. Great job. Before we move on, I want to show you one other way to do this. Okay? I know, and that's okay. You can grab a sticky note or you can just watch. But on the homework, I showed you something that started with grams divided by liters. Is this what you were asking about? Where it started with grams divided by liters? When you said switched around?
Yeah, it started
Yeah.
with the grams and then it went to
Right.
It's the
So
last one. It's
I-
number 9. 9 had it switched around.
Yeah. So I'm gonna work it through this way, but it's the exact same thing. Take a look at the board. Okay? All I really did was I started with, I know they gave me 10 grams of hydrogen fluoride, and eventually I would divide that by 2 liters of water because I'm dissolving it in there. And then take a look. I can put every step here together. I can convert grams to moles. I can convert moles of hydrogen fluoride to moles of H3O plus and end up with the concentration I'm looking for. So I'm just putting all these steps together now. Grams of hydrogen fluoride. We said it was 20 to 1 mole hydrogen fluoride, and then I can convert that 1 mole of hydrogen fluoride. We know that 1 mole of hydrogen fluoride equals 1 mole of H3O plus. Okay, if we cross out units, we end up with moles of hydrogen fluoride divided by liters, which is molarity. So that's going to give us 0.25 molar hydrogen fluoride, and then you just estimate pH the same way we did here. So this is the exact same thing as what we did above. It's just really, really condensed. Okay, and so this problem that we just did is all of these 7, 8, and 9 on this page. Okay, we just did it a much more condensed way. Okay, what questions do you have? Where are your gaps on this?
You mentioned me a little bit.
Yeah, happy to. Where are your gaps on this process? No gaps? Feeling good? Yeah? Okay, so you gotta tell me. That's what this time is for. We've got so much time. The whole thing? All right. Let's start up at the top then. Okay. I'm telling you, I have a powder. The powder is made of hydrogen fluoride. Okay. What do we use for powder here? I'm gonna use.
There's salt in
You have salt? Incredible. Where is it?
blue.
There we go. All right, so I have hydrogen fluoride. It's just a random chemical. Forget that this says salt on it. Okay? There's my hydrogen fluoride. Okay? That's about 10 grams of hydrogen fluoride. We feeling good so far? Okay? I am now going to take this hydrogen fluoride and put it into this cup of water. We're going to pretend this is 2 liters of water. Is that all right with you? I mean, it's clearly not, but I wasn't that thirsty anyway. So here we go. Scoot this over here. I got my water. I got my hydrogen fluoride. I'm going to put this all in here. Okay, wow, that is a salty paper. Okay, so now what I'm asking you is, what's the pH of this water? Well, the only way to figure out pH is to know the concentration of hydrogen ions in this water. Okay? And the only way to know the concentration of hydrogen ions in this water is to know how many moles of hydrogen ions were divided or were dissolved into how many liters of hydrogen ions. Or, excuse me, how many liters of water. Okay? Basically, I'm asking how many molecules of hydrogen ions are in there and how much water are they diluted in. Okay? More water means it's going to be a lot less strong. Less water means it's really, really strong. It's kind of like when you make like those mixed drinks with like the Crystal Light or the Kool-Aid. If you put a ton of powder, a ton of moles of something, and just a little bit of the water, it gets really, really strong. If you go the other direction and you end up with just a little bit of something and a ton of water, you end up with something that's really weak. Okay? That's fine. So that's what we're doing here. We're saying, okay, I know how many grams it was, but how many molecules was that actually? And once I figure out how many molecules, okay, how much water did I put it in? Okay, so how concentrated is this? How strong is the drink, basically? And that's how we figure out pH. Okay? Any specific questions for me? All right, we're going to do one more problem. We're going to do 118, and I'm going to do it. I'm actually going to give you a choice. Do you want us to work through it together with the steps? Steps? Or with no steps? Steps? Okay. So I did a bad thing here. I left off a step. And that first step matters. See this at the top? We're going to have to make sure it's balanced. But first, let's read the problem and see what we're doing. Anybody have a pool at home? Nobody? When you do, you have to put chlorine in it. Otherwise, bacteria grows in it. It's unsafe to swim in. Anybody been to like the public pool? No, it's too gross for people.
One.
The neighborhood one?
Yeah.
There's so much chlorine in those. It like hurts my eyes to open my eyes underwater. Yeah? And that's because they put a ton of chlorine in there to kill the bacteria. This is a thing that people consider too in emergency response teams. They have to make sure the water is safe for people to drink, because if there's just been a hurricane, if somebody's toilet pipe burst and there's gross things in the water, like we still have to drink something, so we have to make it safe. So chlorine compounds are often used to disinfect water by killing bacteria while remaining safe for human consumption at low concentrations. So as long as we don't have too much chlorine, we can still drink it. A common way to do this is to create hypochlorous acid, and that happens when chlorine is dissolved in water. So we can put a chlorine powder in water, or gas, in water, and it will make that hypochlorous acid and H3O+, which is going to make the water a little bit acidic and kill some of those, the hypochloric acid is going to kill the bacteria, but in the process it makes the water acidic. We can only drink water that's so acidic. So the problem asks, after a hurricane contaminated the local water supply, an emergency response team adds a disinfectant powder to disinfect the water. There's 10 grams of chlorine in the water, and it gets added to 5,000 liters of water.
Did you say 10?
Oh, excuse me, 25 grams of chlorine, and it's added to 5,000 gallons of water, liters of water, excuse me. Assuming all the chlorine reacts, what's the final concentration of hydronium ions? And thus, what's the pH of the water? Basically, is it safe for us to hand to people to drink? So, first we got to balance this. So, let's balance it. How many chlorine on this side?
2.
Okay, how many chlorine on this side? Whoops, that should be a lowercase l. 1 on this side. Okay, so we need to put a 2 here. Now we've got 2 chlorine over here and 2 chlorine over here. Great. How many oxygen on this side?
1.
1. How many oxygen on this side?
2.
2 plus a third, right?
Oh, yeah.
So there's 3. So that means we need 3 oxygen over here, so we need to put a 3 right here. All right. How many hydrogen on this side?
2. 5.
Oh,
Wait. Yeah. Wait.
So there's 2 of them normally, but we've got 3 of these molecules now.
5.
No, 6. Because there's 2 of them, so we've got water like this. But we don't have 1 of those molecules, we have 3 of them. So I'm going to draw it again. and we say 1, 2, 3, 4, 5, 6 of these. Okay. If you're having trouble with this, we've got some practice problems on this on page, well, we've got a bunch of them on the Stoichiometry party Padlet, but there's also a bunch on page 72. If you're struggling on this, it's time to go back to 72 and watch some videos on balancing equations. So we've got 6 over here. How many do we have over here?
Of the hydrogen?
Mm-hmm.
2, and then the 3.
That's right. 2 and 3 is 5. Gosh, this is obnoxious to balance. All right, what should we do?
Throw it out.
Throw it out.
We put, never mind.
Yeah, honestly, you just keep going. You just keep adding, and it's okay. So we've got 6. So let's double check. We didn't make a mistake. 2 chlorines, 3 oxygen, and 3 oxygen. Good. 6 hydrogen over here, 5 over here. Well, we have to either increase the amount of this or the amount of this, okay, to make this work. If we change this to 3, it would balance. But then we'd have more oxygen that we would have to account for. Then we'd have 3 plus 1 is 4 oxygen. Then we could change this to 4, but that also changes the hydrogen again. So my suggestion is let's mess with this one instead. Let's try it. Okay? So if I put a 2 here, now I've got 6 plus 2 is 8. Hydrogen. Oh, we're going to have to do the 4 anyway. So we've got 4 of these, so that's 8 of these, 8 of those. 4 oxygen, 5, 6 oxygen. Oh, bugger, this one's really obnoxious. All right, we're going to have to do this the big kid way. I'm sorry, y'all. I tried to do it in my head, but it turns out these are just really hard to do in your head. So we're going to pull out the full sticky note and give it the full treatment. Okay. All right. Anybody else want a sticky note? Yeah. Here you go. Ta-da. Absolutely. Catch. It worked though, right? It sort of twisted around. Sorry about that time I hurt you. Okay. We've got chlorine. We've got hydrogen. We've got oxygen. We've got chlorine. We've got hydrogen. We've got oxygen. It's possible I just made a mistake. Doing these in your head is really hard, and I don't suggest it.
Wait, what did you say it was?
Hmm?
What are the numbers?
What are the numbers?
Oh, never mind.
Yeah. So we're gonna start over on this one because these are they're hard to do in your head. Sometimes you can try it, but when you start to lose track of what you're doing, it's time to just do it the difficult way. Okay. Let's see, we've got these chlorines. There's 2 over here, so we're definitely going to need 2 of this. But let's count them up first. We've got 2 chlorine, got 2 hydrogen, 1 oxygen, and on this side, 1 chlorine, 4 hydrogen, 2 oxygen. So one thing we're absolutely going to have to do is put that 2 here, just like we started out with. It's going to make us have 2 chlorines, 3 oxygen, and 5 hydrogen. Emma, am I missing something? Or does this one just suck?
Well, what is usually a cue to me is it's going to be very hard to balance something with even subscripts on one side and
Oh, that's a good point.
odd ones on the other side. So
Yeah.
I typically try and double the ones on the right so that they all become even.
Oh, that's so clever. So you're just putting a 2 in front of everything on the right,
Yeah.
just to start it off. Okay, so
Yeah.
we're going to put a
So
2
then
here
it's
as well.
all even numbers.
So 1, 2, hydrogen plus 6 more is 8 hydrogen now.
Does that make sense?
Yeah. 2 plus 2 is 4 oxygen, And chlorine we've still got 2 of. Okay.
That's typically where I
Oh,
start
that's so
because
clever. Look at
it's
this.
so frustrating otherwise.
All right, folks. We only need one more number. Wow, I have never heard that in all my years of chemistry. So if you've got odd subscripts on one side and even on the other, it's going to be hard. So you just multiply this entire side by 2 so that everything on this side ends up even again.
And you might need to go around and play with some things, but it usually makes it easier.
No, that's super clever. So now what can I do to make these numbers work out? Our chlorine is fine. All we have to fix is the amount of hydrogen and oxygen. Right. If we put a 4 right here, 4H2O, this becomes 8, this becomes 4, and we're done. Oh, thank the Lord.
Yeah, and then you at the end check if anything can reduce because you potentially made the whole thing.
Right. So if you ended up doubling the entire thing, what she's saying is you might have to divide everything by 2, but since this one at the front is a 1, we're fine. So I'm going to rewrite this nice and pretty so that we don't have to look at the ugly one. Not that there's anything wrong with him, it's just a little much for me visually. So we're going to do Cl2 plus 4H2O yields 2 HOCl plus 2 H3O plus. I promise you, there was probably a chemistry teacher desperately trying to teach me to just double both sides back in the day, and I was just not listening.
I didn't get that until I was teaching it.
Isn't that brilliant?
just
Or just to
kinda
double the
figured
one
it
side? It's really clever.
Anytime you see subscripts that are like
Yeah.
3 or odd.
Even on one side, odd on the other. That's super clever. Okay, so we've got it balanced now, and now we can move on with our lives. Also, just so you know, if anybody needs to go at any point, you can just walk out. You don't need to get awkward about it. It was supposed to be over 4 minutes ago, which is why I just said that. It'll probably take us 10 minutes. We'll probably be done at 4 o'clock on the dot. Okay? So here we go. First thing, let's find the molar mass of chlorine so that we are ready to convert grams of chlorine to moles of chlorine. So this one should be pretty easy. Cl2 is just chlorine bonded to another chlorine. So we've got 2 of these. So the molar mass is going to be 2 times whatever chlorine weighs.
35.45.
Okay. Chlorine weighs what'd you say?
35.45.
0.453?
Well, yeah, that's the whole thing.
That's the whole thing. Okay. And that's grams per mole. So when we do that, we're going to find out that chlorine, its molar mass, or chlorine gas's molar mass, that's called diatomic. Okay, clear. Let's do 2 times 35.453. We have 70.906 grams per mole. Okay. So now we're ready to convert the grams of chlorine to the moles of chlorine. How many grams of chlorine did they put in the water supply? 25. Very nice. So we've got 25 grams of chlorine. And we need to convert grams of chlorine to moles of chlorine. How are we going to do that? When in doubt, you do the multiplication symbol in the new line. Once you've got the new line, you already know what goes on the bottom. What goes down here? Right. It's whatever is the same as up here. So it's going to be Cl2. We haven't changed that. And what is it going to be? Grams or moles?
Grams, because we're at the cross.
That's right. If grams was up top here, it's got to be grams down here on this one. And we're trying to convert to moles, and we know we can convert grams to moles because what this means, the 70.906, this is like saying 70.906 grams of Cl2 is the same as 1 mole of Cl2. Okay? Those are equal. So if they're equal, we can put 70. I'm rounding now because I ran out of space, 70.9 and 1 mole. Okay, and the grams will cancel out. Grams of Cl2, grams of Cl2, and that will leave us with moles of Cl2. And let's do that math. 25 divided by 70.9.
They gave us 0.3.
That's what I got. 0.35 moles of Cl2. Should I be more careful in my rounding? Probably. Do I care right now? No. Right now we're just trying to figure out the concepts. So now we've got moles of Cl2. This is the version of the quiz that gives you steps for each problem. So the nice thing is you complete the step and you just move on to the next one. Now it says convert moles of Cl2 to moles of H3O+. Well, we know the moles of Cl2, they're right here. So we can do 0.35 moles of Cl2. What do you think, Ari? How do we convert that to moles of H3O+?
Do the multiplication thing.
Okay, dimensional analysis.
Yep.
Okay, what now?
Then put the H3O plus on the top.
Okay,
Moles on the bottom.
moles of what?
CO2.
Good. And if we're changing the substance, we should stick to moles.
Yes.
You can only change one of these things at a time. You can change the substance or you can change the unit, but you can't change both. So if it was moles of Cl2 up here, it's going to be moles of Cl2 down here. And if it was moles down here, but we're changing to H3O+, then it needs to be moles up here, so that only one changes. Now, let's take a look up here and see what the ratio is. When you're going moles to moles, the good news is it's already been figured out for you, because that's what this chemical reaction is. So you tell me, how many moles of Cl2 equals how many moles of H3O+? Okay. Ari, what do you think?
Say that one more time.
Yeah, how many moles of Cl2, if I put in, for example, I'm trying to ask this in a way that doesn't give you the answer. I want to put numbers here to convert from moles of Cl2 to moles of H3O+. What number should I put there? It's a little bit like a recipe. Remember, like 1 graham cracker makes 1 s'more? So what are the numbers on this one?
2 on the top.
2 on the top for the H3O+. And on the bottom?
1.
Right. And that's because there's an invisible 1 out here, because we've got 1 molecule of chlorine gas, or chlorine powder in this case, yields 2 molecules of H3O+. So we've done that. I think that math is doable in my head, because we're going to do 0.35 times 2 divided by 1, so that should end with 0.70. Is that correct?
Yes.
And that's moles of H3O+. Okay? Next, it says determine and then it says H3O+ in brackets. What does that mean?
Concentration.
Very nice. Concentration of H3O+. Anytime we're doing concentration, I want you to think of like Crystal Light or Kool-Aid. All right? We're always going to be doing some amount of substance in some amount of water, at least in this class. So, how much of this substance do I have?
20.
Well, originally we had 25 grams, but we converted that
Yeah.
to moles of H3O+, right? We have 0.70 moles of H3O+, and I'm going to dissolve that in how much water?
5,000.
That's right, 5,000 liters. 5,000 liters of H2O. This matters because we're trying to get water for a lot of people who have lost access to water during this hurricane. So, if we do this math, this is going to give us moles per liter, which is perfect because that's what concentration is measured in. So we're going to do 0.7 divided by 5,000 liters, and we get 0.00014 moles per liter of H3O+. We could have just written capital M. That's the same as moles per liter. That is not a lot of H3O+. That's very, very little. The question is it too much? Can you convert that to scientific notation to find out? Go ahead.
1.
Okay, so we're going to convert that. It's going to be 1.4 times 10 to the what? We're going to do 1, 2, 3, 4. Negative 4, there you go. Negative 4, and I'm doing capital M this time. It's the same thing as moles per liter. H3O+. Now, Bella, this is the part you were coming for. I've got my concentration of H3O plus now. How do I estimate the pH from that?
There's a formula, right?
You could do a very fancy formula, it's true. However, we have a way to estimate it that's significantly easier. Let's move back to that page we were on a little bit earlier. If I know my concentration of H3O plus is 6.0 times 10 to the negative 2, yes, I could teach you logarithms.
Oh, okay, so it's -4.
That's right. All we have to do to estimate this is we can look at the exponent. Is it perfect? No, but it will definitely do. And to be honest, I am not taking the bullet for your math teachers and teaching you logarithms. So,
I don't think I ever knew that.
isn't that great?
I had to know that.
Isn't that great? We used to use it just as like a way to check our math. But yeah, now
It just
there's
isn't always the.
yeah. Now there's some sneaky stuff you can do with this number right here to see if it's closer to 4 or closer to 5. But like, who cares? So it's about a pH of 4. Wow, this is so great. We both taught each other something today. This is incredible. All right, so we've got a pH of about 4. Now, we want to know if these poor people who have lost lots can drink this water. Can they drink it for a little while? Probably, but we don't know how long there's going to be a hurricane, so let's read on. The U.S. Environmental Protection Agency recommends that drinking water have a pH between 6.5 and 8.5. Is the water treated by the emergency response team safe to drink? What do you think?
No.
No, this is not between 6.5 and 8.5. Okay? In fact, if it needs to be as low as 6.5, that means the concentration of hydrogen ions needs to be less than 0.12345 moles of H3O plus per liter. So that's a lot less than we've got right now. We got to cut that down a lot. So that brings us to the last question. How can we make the pH of water above closer to a neutral pH?
Grams, what is the measurement at the very end?
Moles of H3O plus per liter. Yeah, so we've got way too many hydrogen ions in here. Okay? It's making the pH really low. We want the pH to be higher. What can we do to raise the pH?
Hydrogens from the water.
The hydrogen's from the chlorine that we added. The chlorine dissociates to produce this acid, which kills the bacteria, but it also makes acid. Huh? So that's the logical thing, right? If you want this to be less acidic, we could just add a bunch of water. The problem is we don't have safe water to add. For every new water we add, we have to add more of the chlorine, which leaves us in the same spot. So what can we add that will counteract these? Here, what's the opposite of an acid? A base. So let's look back at that same page again. We've been on page 112 a lot. We've got too much H+. We want it to be more alkaline, like a base. What can we add? Okay, so we have to add something that will add OH minus. Add OH minus to neutralize. The pH, absolutely, that's one of our options. We could also add anything that is happy to accept an extra hydrogen ion. But let's start with this. What things do you know that have OH minus in them? Let's take a look at our last lab. What do we got here? You see anything with OH minus in it?
Oh, I see. OH.
Okay, so barium OH, or barium hydroxide is a bad choice because barium is really, really, really dangerous and actually attacks the human reproductive system.
What
So
about salt?
we could add NaCl, but that doesn't actually have any OH minus in it. We want something with OH minus in it. Okay, if we add sodium hydroxide, it will add sodium to the water, but the hydroxide will counteract it. How do humans do with sodium in their water? Or how do humans do with sodium? Do we worry about having too much of it? Yeah, so we'll put that one on hold. It's possible, but we want to avoid too much sodium.
What about KOH?
That's potassium hydroxide. How do we feel about potassium in our water? Maybe.
Like the banana stuff.
Yeah, like the stuff in bananas. So maybe potassium. Calcium hydroxide, how do we feel like calcium in our water?
Calcium.
So that's our quest. That's what we need to do. Either I would recommend NaOH or KOH or calcium hydroxide. Okay. The question is, which one of these would be the least dangerous for humans to have in the water? And you could find out exactly how much was going to be in the water by figuring out how much OH you need to remove those extra H3O pluses and neutralize them. That would, and you could backtrack and figure out how much calcium or how much potassium or how much sodium was there, and you could cross-reference that with how much a human can actually handle. So that is how we would solve that problem. Ladies and gentlemen, let's be done. Okay, you did a really nice job. I'm going to stop this recording and I'm going to put it online for you.